Welcome back to the Swayam course on Introductory Material Science and Engineering. Today, this is sort of the plan that we have for the session. So there will be a note to teachers. These will be instructors of Material Science and Engineering from a wide range of institutions. We will have a recap of the very first session that we had here. And part of the recap will be telling you a little bit more about the space that we have set up here at the Teaching Learning Center, IIT Madras. Then there will be something which in the world of active cooperative learning is called guided reading session. So there will be some handouts that will be given to the students and they will be made responsible for that reading, and they will be told what the highlights would be or what the cornerstone ideas would be that they should focus on, and accordingly they will be asked questions using which there will be some discussions that will happen in the class. And finally, there will be a student-led summary. So this is timed for about an hour. So before we start, we will of course recapitulate what we learnt about this space here. So this space here, as you can see, is brightly lit. It is acoustically reasonable. In fact, you can hear my voice very clearly precisely because of that. There's no much echo and so on. The place is such that people can actually sit around round tables and have their discussions. So this particularly facilitates active cooperative learning. Not only that, it is technologically enabled. By that what we mean is we have computers that are around, and the space is, as you can see, fairly comfortable and hence quite congenial for a teaching learning experience. So the few things that I want to actually now point to and perhaps ask as questions that might motivate teachers who are attending this particular course would be the following. So the first one you already have noticed, so that is observing the ambience here in Teaching Learning Center. The second one is a question for all of us who do teaching of one form or the other, instructions of one form or the other. How could we as teachers change the settings in our own classroom? And this is a very relevant problem even for me, because our classrooms are very rarely like this. So I think this is an ongoing discussion, and we have to think about ways in which student activities can be encouraged despite the physical infrastructure that exists in our classrooms. So we ought to think about this, all right? And another thing is that is worth thinking about is how do we give time to our students so that they have time to reflect and think and consolidate the lessons that they have learned through their sessions or classes. Very often we teachers, we run through the syllabus or the curriculum rather quickly, but that doesn't provide the student an introspective experience, the kind of experience that is likely to inform the student's thinking. And I think it is very important for us to give time to consolidate lessons even within the class, not just outside of the class. This one is a question I have been asked very often during FDP sessions I have conducted here in Teaching Learning Center, and that has to do with large classroom management. Now, when it comes to large classroom management, there are a few tips I can share which might be relevant, and this is also available out there in various educational platforms. Some of the things that might be given is relevant for places where there are substantial resources, and then there are some places where there may not be many resources, in which case again we need to think about enabling large classroom management and effective classroom teaching. So a few things that I can think about is decentralizing the educational space. You know, in large classes it's very hard for the teacher to reach out to all the students. It's quite proven that large classes are actually a little harder in many ways when compared to smaller classes. However, if we have a decentralized space like this, wherein students are asked to come together such that students of different, let us say, motivation levels or interests are actually put together, then students who are a little ahead in the learning curve can help the other students who might be a little behind in the learning curve, and hence you set up a relatively flat and even playing field. And you could think about ways by which you could use the time and talent that is available in class in order to facilitate learning, even in a large classroom setting. In a setting like ours, which I must admit is relatively better in terms of the availability of resources, we can use TAs, for example, in order to facilitate this kind of decentralized education and learning. In places where that is not available, again, distributing talent, basically making sure that students at different levels within the learning curve, different experience are actually distributed so that the one who has a little bit more experience helps those who have a little lesser experience and so on. So I would say that is by and large a strategy that can be employed. on a need basis, so that you facilitate good education, good learning environments in a large classroom setting. I wouldn't say that it is not fraught, it can come with its own challenges, but I think that might be a good experiment that through which there can be some learning that teachers can get and which can actually inform their large classroom experience. So with that, I will move to the content part. Perhaps even before moving back to the content part, I want to just talk to you about these three words, because those of you who teach might actually benefit from knowing these three words. Pedagogy, which basically means systematic instruction in a manner such that a discipline is taught well, effectively. Andragogy, which is mostly the situation here because most of the students here are adults. So andragogy actually represents enabling adult learning, helping adults learn, and this is particularly because teaching children can be different from teaching adults. Adults might have well-formed personalities, learning styles and so on. So andragogy takes into account that. And the last one is heutagogy, which is very important for teaching at the MS PhD level, because students who come for MS PhD typically are self-driven, self-motivated and so on. And the role of the instructor there is to sort of provide pathways so that they learn and provide enough guidelines so that there is some self-directed learning. So these are three words that might be relevant for you. Regardless of which educational institution you are in, you might find these three words rather relevant, and there is plenty of literature available both in engineering education as well as higher education in general that cover the spectrum of these topics and themes. Okay, so let us come back to the content part. All right, so a quick recap, and maybe I can do the recap here, and then this is entirely reasonable because last time they helped us with the summary. So the recap is the following. We looked at what I think is a reasonable definition for material science and engineering. We looked at it as a syncretic discipline, that means a discipline that has emerged because of many other disciplinary traditions. We looked at the fact that it derives from metallurgy, ceramics, solid state physics and chemistry. So it is truly a fusion discipline, a convergence discipline, and I took this definition from the writings of Professor Rustam Roy, who happens to be a professor of material science and engineering at Penn State. So what you learned in the last class, okay? So what you learned in the last class is an overview of the origins of material science as an academic discipline of study. So where does it come from? What is its history? We in fact had an overview, but at the same time you saw that the tradition at least has a fairly longish history, though as an academic department it came together only in the last century. The truth is it has a fairly long evolution and it has evolved over time to meet the needs of the then science and technology requirements of that particular era and time. But it was clearly understood that by around 1940s we needed an exclusive discipline on engineering materials, the science of engineering materials, and hence material science emerged as a discipline by its own right. Then we looked at convergence and interdisciplinarity, the prospects of the field, and students here looked at materials tetrahedron. They used it in order to come up with a project design. So these are at a first level, I would say, very helpful because students immediately see that what they have learnt in the class has relevance outside of the class as well. So the materials tetrahedron was seen as a thinking tool, as a tool that enables a certain kind of deliberation about projects in a structured manner. And then we looked at current materials classification schemes and introduction to project design in materials engineering. So all of this of course is at some level a partial response to the grander question. Students who might enroll for a course in materials engineering or who major in materials engineering or science might ask, why should I study this? So all of this is at least a partial response to that particular grander question. Okay. So I have also earmarked the relevant reading material for those of you who are listening and for your students. The reading material that maps to what we have done in the last session is taken from Callister's book. This is now available in Indian edition, so I don't think most of you will have any difficulties in getting it. Most of your libraries at the very least can procure it, and these are the sections, and this is the approximate reading time that I think corresponds to the discussion that we had last class. So technically we have as a consequence covered about 2 hours of ground of around 1 hour here in the classroom, and then 1 hour of reading basically follows thereafter. So today's class will be on classifications, the current classifications of engineering materials. We have already looked at categories of engineering materials, but we have not studied them in great detail, isn't it? We do not know precisely what those classifications point to. And then we will look at physico-chemical properties and engineering parameters for materials. Very important, because whenever you choose material, these are the first and most fundamental things you have to look at. What are their properties and what are the parameters? Suppose you are designing a material for a specific application. What is the performance parameter that you are looking for is something that you should be able to choose for yourself and look for the corresponding material. So engineering parameters become very important. So I will talk to you about these parameters, define these parameters for you. And here in the class we will do a simple graphing exercise. And this is particularly important because you might observe that about 80% of any given material science department has experiments going on. So 80% of the activity tends to be experimental. So students of materials engineering and science, they tend to do experiments. So they should have some confidence of plotting it, observing trends and so on. Okay. So this will be a graphing exercise, and this I took from an engineering education website called Instructables and from an author called Philip Figari. It's a very simple graphing exercise, but it teaches students about the most important features of a stress strain curve. Okay, so typically teachers draw the stress strain curve in the classroom and then say that these are the points and so on, but here maybe we can get these students to deduce it or provide some information and then get students to engage in that particular material, and then they get to see that graphing is a very instructional tool. It's a tool for thinking, in fact. And the reading material that corresponds to what we are discussing here is assorted reading materials from the following. There is material science and engineering. These are the sections. Okay, so you will find that today's reading is a little bit bulkier, but not all of it will be covered today. But eventually we will cover a certain amount of ground. But this is the reading that maps to the discussion that we will be having today. All right. And there is another book, and this is an Indian book, and hence I think very affordable even for students. So this is by Professor M.R. Srinivasan. The first chapter actually corresponds to what we are going to discuss. So either students can read this, so which is basically a set of sections from here and there within Callister, or this, and they would more or less have the mapping with this particular session. All right. So before we go forward, I would like to ask the students here a question. So what do you mean by classification? What do you mean by classification? Very simple question, right? Very simple question. And why is it relevant? What do you mean by classification? Why do you think it is relevant? All right. Alternatively, you can ask, in your own life, do you do classification to organize information in your head? Okay. Because see, the world of materials is so diverse. You look around, there are gazillion materials around you. Why do we need to classify? What is the need for classification? What advantage does it give you? And have you done classification for that matter? All right. So just let us focus on the first question. What is classification? Why is it relevant? All right. So why don't you discuss that? And I will also ask you to discuss the second question. Give some examples wherein we human beings classify in order to organize information. So just discuss these questions. And you can come up with any example of classification. Absolutely any example or examples of classification. It's up to you. Okay. Yes. Please discuss. So you can take maybe 1 or 2 minutes. I will go around, give hints, and we will see what you are thinking. So I have given handouts corresponding to the discussion that we are going to have. Now in places wherein there may not be sufficient resources, you can probably print out just enough handouts so that every table will have one handout each, so that every table would have at least some material to refer to. So that they can base their discussions based on the material you provide. So you scaffold their discussion, all right? You understand the question. So what is classification? What is meant by classification? What is the advantage that it provides? Can you think about some situations in your own life or wherein human beings in general classify information? Okay, do you understand the question? Okay, good. So the reason why these questions are given is because students come from a wide range of backgrounds. Sometimes we might use words like classification, definition and so on, but they may or may not come from a background wherein they understand what we mean in a setting, including in our own setting wherein students come from a wide range of linguistic backgrounds. So it's a good idea for you to sort of evaluate, to see whether your students understand what you are saying, and if there is a language barrier, eliminate that language barrier. Right? So that's really what I have attempted to do here by asking them what classification means even before talking about materials classification. So you're making some progress?
Yes, sir.
Good.
So we think that classification is nothing but dividing something with respect to their specific
Some properties. Okay. So basically creating classes, you know. So in mathematics you have studied set theory, you know, you define sets and the members of the set have some specific property, for example. They are connected to one another in a very well defined manner, right? So arrangements, classifications are very common, isn't it?
Yes.
Very good. Even numbers, when you studied numbers, you classified it into even numbers, odd numbers. When you studied natural numbers, you divide into even and odd and so on, right? So classifications are very meaningful because it helps you think clearly, categorize information and facts in a very reasonable manner, correct? Yes?
Whatever you said, like based on the inherent properties of the things, just classify.
It need not be just material, right? It can be any group of information. For example, organic chemists might actually classify compounds. Material scientists might classify materials. Library scientists might classify books, right? So based on the specialization and the object of their study, people could actually classify information. All right, and it's very helpful because it enables you to structure the information that is present. Otherwise, that which is a scatter basically comes together in the form of structure, and you can actually start developing knowledge trees based on that, right? Otherwise, it's a little hard to grapple with the diversity of information that is out there. So the key is information is very diverse, correct? So I might do the tensile stress test, let us say, which is some test, okay, that is relevant for determining the mechanical properties of material. I might choose to do that on different materials, a gazillion materials around, and you would have a large number of graphs. But it wouldn't be meaningful unless and until you say, you see, I can divide these graphs into this category, and this category. Then immediately, what is otherwise a very disorganized bunch of information becomes classified in a very neat category. And those neat categories actually enable us to think with clarity. So clear thinking is very critical for science, the business of science. So what is classification? It is simply arrangement of a group of items into classes or categories according to some shared qualities they may have, right? They may have something, let us say characteristics, properties, some parameters associated with them that they share, and hence you can classify them in a particular manner. And can you give one example? What is the example you thought of? Periodic table, okay. So basically classifying elements into rows and columns, right? So saying that if they belong to this particular group, all of them have the same valence state, they will have similar chemical properties and so on. As you go from left to right, it becomes progressively less conducting and so on. So you actually start seeing that by classifying materials, by classifying elements in this particular case, in the form of a periodic table, you are able to immediately look for shared trends and vice versa. When you classify materials based on their shared trends, I can find substitutes, is it not? Instead of using sodium, maybe I can use potassium. That's right. So I can, as a consequence, come up with solutions to problems that might exist because I now have structured information. Without structuring information, thinking about solutions becomes very challenging, right? Did you think about an example of classification? Library is a very good example of classification. Yes, very, very many kinds of books, but you classify it into very many different categories, then it becomes easy for you to look for information in the right manner, correct? So very good. So that's absolutely right. So the two examples you came up with is periodic table and library. Very good. Fantastic. And by the way, periodic table is a very nice tool for material scientists. Alright, it's a tool not just for chemists but also for material scientists, progressively for condensed matter physicists and so on and so on. Okay, now let me help you through some guided reading. Okay, so we are going to look at some engineering materials. I have written some text and I'll highlight some parts of the text as I actually scroll down through the text. Focus on those highlighted parts, write down some notes based on that, whatever captures your mind, your imagination, alright. And then I will ask you to recapitulate slowly and maybe also give you some props so that you recall what you have actually read, alright. So the first one is the following question: mention attributes of metals, ceramics, glasses, polymers, elastomers, semiconductors, liquid crystals, composite materials and nanomaterials. So these are a fair number of terms, isn't it? So I will give you the definition and the corresponding materials properties and the ranges corresponding to these particular materials, alright. And then what we will do is I will expect you to make some salient notes, note some keywords, look at salient points, alright. And most importantly, would you consider this to be some form of materials classification? Of course it is, because when I say metals typically have a high yield strength, high Young's modulus, that basically immediately enables you to say, okay, if I run into a metal, it's likely to have a high Young's modulus. You understand? It's likely. So you immediately are able to rationalize simply because there exists this category, alright. So let us now spend some time just reading about metals, and then we will discuss about the metals around this, alright. So this is a small note on metals. So it has high Young's modulus. Note the SI unit. What is the SI unit here? I have written it as gigapascal. The SI unit of pressure is Pascal. And what is Pascal? Newton per meter square. So this is important for all of you to know. So the SI unit of pressure is Pascal, and Pascal is Newton per meter square. Okay. And what is pressure? Pressure is force per unit area. Very good. So this is basically force per unit area. Alright. So if I take a material and for a particular reason I am going to draw it in a manner, this is called the dog bone shape. Okay. And I am going to actually fix this, I am going to clamp this end of this material. So this is the material. Okay, and I am going to clamp this end and I am going to pull it. I am going to pull it. Okay, so this material you expect it to elongate a little bit, right? Because I am pulling it, I expect the material to elongate a little bit. Alright, so now my question is, if I know the force that I am putting and I know the area of the material, can I find out the pressure that is acting at any given cross section? Absolutely. So I know the force per unit area, and that in this particular context would be called stress. That would be called stress. So if pressure has the unit of Newton per meter square, what is the unit of stress? Again Newton per meter square, hence pascals. And giga stands for 10 to the power of 9. Alright. So when I say 40 to 400 gigapascals, what is that in terms of a power of 10? 4 into 10 to the power of 10 to 4 into 10 to the power of 12 Newton per meter square. So it's really high. Okay, it's really high. So you have to apply substantial amount of stress in order to achieve a certain kind of deformation. Okay, so metals have a high Y. Y stands for Young's modulus, and Young's modulus is basically going to be this stress divided by the corresponding strain, where strain is basically the change in length per unit length. So we are going to define epsilon as change in length divided by unit length. Let me say that the piece of material looked like this to begin with, so that is L, and then you apply the stress, it basically becomes L plus delta L. So delta L divided by L will be the strain. By looking at this formula, can you tell me what the unit of strain is? It's perfectly dimensionless, right? So this is a dimensionless quantity. So if this is a dimensionless quantity, the stress by strain, what will be the dimension of that? Again Newton per meter square, and hence the unit of Young's modulus is pascals. Okay, here it is 40 to 400 gigapascals typically for metals. Alright. Okay, so the next word, ductile. What does ductile mean? Have you heard this word somewhere? What is ductile?
It will undergo some deformation before it fractures.
What's that?
The material will undergo some deformation before it fractures.
That is right. That is right. So can you think about, that's a technical definition, but can we connect it to our daily experience? Can you tell me some ductile materials and the form that that particular material has taken by virtue of the fact that it's ductile? So we human beings, we are good at utilizing the properties of materials to give shapes to the materials. So give me an example of a material and the shape it has taken up, okay, of course through human intervention, but that intervention is actually facilitated because of ductility. What will be one example? So I have some material. This has the shape it has because some human being gave this shape to it. Okay, so I am saying, let us say ductile means whatever Naveen has said. So is it possible for you to think about an example wherein a material in the form that it exists was made possible because of its ductility?
The chairs we have in such a way that it deform certain shape.
Yeah. Yeah, so that's partially right. I mean, the casting of some of these things requires a certain kind of deformation, but the simplest example would be wires, isn't it? So if you look at electrical wires, very often they are called drawn. The process is actually called drawing. They are called drawn wires. So you take a piece of metal and then you draw it. Okay, so this drawing is entirely made possible only because it's ductile, not otherwise. If it was brittle, then it would be different. Bricks are brittle. You try to pull it beyond a certain point, it will just come apart. It will not deform much. But metals, on the other hand, they actually deform. Okay, so they can deform very readily, and as a consequence, you can draw it into wires. Drawing is made possible because of the ductility of metallic wires. For example, the zinc, copper wire and so on that is actually available for electrical wiring, they actually function entirely because of this. Okay, so a large number of not just metals but metallic alloys actually can be drawn. They are ductile. All right. Okay, the next word, malleable. What is malleable? It is a related term. Okay, it's a related term.
Giving some different shape.
Malleable.
Under compressive stress, it is undergoing elevation.
Yes, that is right. So he's correct. In fact, can you think about an application for this? So I have a metal. I know that I can actually apply compression. See, ductile behavior was under tension. Now I have to explain to you malleability. So can you give an example wherein by rolling a material, I basically get a sheet. So many metal sheets are available, right? Aluminum metal sheets are available. The aluminum foil that you use in your kitchens, for example, they are rolled. Okay, a lot of sheet metal that you might be using in your workshops and so on, they are rolled. So you cannot create such rolls out of ceramics that easily, isn't it? Because ceramics would just get powdered, they would get crushed. Metals, on the other hand, you can actually render them in sheets. So sheet forms can be actually given to them. All right. Next is good thermal and electrical conductivity. So they tend to be good thermal and electrical conductors. So can you think about one experiment that you could design in order to show this to yourself? Yeah. Yeah. Something that you might use in kitchen, something that you might use in your daily. Yeah, exactly. So you can cook, or you can make coffee or tea in a metallic kettle, right? But then you can't hold the metallic kettle that easily, but you can certainly wrap some plastic or cloth around it, and hence you can actually pick up the kettle. So that is an example of the fact that, number one, the metallic kettle is conducting heat from the stove, and as a consequence the cooking happens. But you can prevent yourself from being burnt predominantly because there is no conduction from the kettle to you, because it is actually it's protecting, the plastic that you are using or the cloth that you are using is protecting you, isn't it? Very good. Some are superconductors. Now before I go further, I want to actually stop here for just a moment. All right. So good conductors of heat and electricity. All right. So can we make some important observations here? I have given you a qualitative word, good conductors. So what is missing here? Some numbers. So maybe you need to take a homework question at this point. So write down this homework question. What are the typical conductivity values for metals, ceramics, plastics, semiconductors, and so on. So this will be a question that I will ask all of you in the next class as a follow-up question. So that you have some reading, some exploration. Feel free to use any search engine you have or book that you have, so on. So engineers and scientists need to be quantitative in the way they think. So here I actually deliberately put a qualitative word because that's what you usually see in a textbook. But when you actually explore, when you actually choose a material, just a qualitative measure is not sufficient. A quantitative measure is important. So you should know that this is the conductivity value, this is the range of conductivity values and so on. You understand? So why don't you look for conductivity values, both thermal as well as electrical conductivity for this range of materials. You follow? So they also tend to be thermally and mechanically shock resistant. That means you punch it, if there is an impact, it still survives. Metals survive those impacts. Ceramics can come crash, they can get crushed when there is an impact. They can actually just splinter if there is an impact. But metals very often, they might undergo deformation, but they do not come apart. So they tend to have very high shock resistance, both thermal as well as mechanical. All right. The next one is load bearing capabilities. Where do you think their load bearing capabilities is relevant? Where do you think the load bearing capabilities of metals are relevant? No, that is true, absolutely correct. But my question is some applications wherein their high load bearing capacities are used. In this building, have we used the load bearing capacity of metals? Absolutely. All the reinforcements that you see in the pillars around and so on, that wouldn't be possible without the properties of metals, isn't it? So in this particular case, it is steel that is used as reinforcement and so on. Next is opaque to visible light. This is rather interesting, and think about why this would be so. Why is it that metals are opaque to visible light? Just think about it, because this connects to something very important called the band theory. Why is it that metals are opaque? Okay, that basically means metals absorb everything that falls on them. They reflect some, there is selective reflection, but they certainly do interact with the full electromagnetic spectrum. Right? They tend to be opaque. They are easy to polish and very lustrous, that all of us know, isn't it? They are lustrous, that means they are shiny. They usually have low creep resistance. What does creep mean? So make note of this word, creep. So it is time dependent deformation. It is called time dependent deformation. Okay, and I will show you some definitions and eventually some curves that might give you some idea as to what creep is. All right. So they usually tend to have low creep resistance, which means if you heat it to a fairly high temperature and if there is a load acting on that particular metal, it starts flowing. Eventually it continues to flow. So creep is a kind of a flow. It's actually time dependent deformation. How much the flow happens depends upon the time over which this particular metal, which is heated to a high temperature, is left. High thermal conductivity and medium wear resistance. All right, very good. Next is ceramics. But before we go to ceramics, can we quickly think about one application that I have not discussed in the class, but which is connected to any one of the properties that is there here. So choose any property and think about one application that you know of which is connected to one or more of these properties. All right. So why don't you discuss before we move further? You understood the question? Just think about one application of metals which is explained by using one or more of the characteristics of metals that is given here. Please discuss with one another. You can share your ideas, observations. You are using metals, including in your pen there is metal. Okay, so metals are all around you. So just choose any one application and tell me what property of metal was used in that application. You understand? So just one application. You don't have to give me numbers or anything. Something that might be there in a car, in a refrigerator, in your specs. Electrical wires, very good. So there, what are the properties we are employing? Conductivity. So certainly electrical conductivity, very good. That is ductility, good.
And that's it.
Yeah, that's about right, yes. So those are the two things that you are using, isn't it? Now it turns out that fuses right? You know what the mechanism of fusing is? Electrical fuses, you know. So whenever there is a sudden increase in the current, the fuse goes off, and that has to do with this low creep resistance. So it's usually a metal wire. You run more than a certain amount of current through it, so the temperature goes up suddenly, and because at such high temperatures it cannot actually retain its shape, it starts sagging and snaps. So fusing basically is made possible primarily because of this low creep resistance. Similarly, in older bulbs, incandescent bulbs, the fusing of the light bulbs used to be precisely for this reason. So tungsten used to be the filament that is used, and that has a fair bit of creep resistance, but still over time it sags, and then there's a shorting event and the bulb fuses. So that used to be the reason why they used to fail very often. That used to be the primary mode of their failure. Okay, yeah. Did you make some observations about uses of metals?
Like that, different type of foam, nickel foam, otherwise the aluminum foam, all these things. We can stretch it, and at whatever shape we want, we can give it, and it also has good metallical and electrical conductor also. It's matching all these things, ductile nature and malleable nature also.
Yeah. So what he is talking about is porous metals, right? Metallic foams they are called. So that's an interesting category of metals, because these are usually made by using foaming of molten metals. You know, you take the metals to a very high temperature until they melt. So they are essentially flowing at that particular point, and then you add some foaming agents which result in evolution of gases. And because these gases are coming out, they actually come out through bubbles, okay? And when they are coming out, they actually leave behind a streak, and hence through the metal you end up having pores. You have large number of pores. So what I'm trying to say is, I can start with a metal block. You know, I can have a metal block here. I can make it a liquid by heating it, and then if there are lots of bubbles that are actually emerging and they leave behind a permanent streak, then you essentially get lots and lots of pores that are interconnected, and this interconnected pore will basically result in something that is metallic in nature and at the same time foam. That's right, that's an interesting thing. But what are the applications that you're thinking of? So metal foams, why would you use it?
It has more pores, you can use it for any energy.
Right, so because they are porous, you can use it to store things, right? So maybe you can use it to store substances, or you can use it to store energy. In fact, maybe both, right? It might be actually a possibility. Yes, and it's a conductor. So the metal structure that it's actually made up of is a conductor. So it can certainly be used as an electrode, wherein there might be a lot of mass transport, or for filling up an electrolyte so that the mass transport is actually controlled in a very specific manner, and so on and so on. That is right. It can be used for catalytic applications, correct? So there might be many applications. So this is a very specialized example that you gave me. Can you think about one very general example? You know, look around and give a general example that everybody who is seeing this video can be able to connect with. You know, because not everybody may be using a foam. So just discuss with one another. So many, you know, are there metals in your watch? Yeah. In your pens? Okay, in the vehicle that you use? Furniture. And so you take any one application, and then what are the enabling properties of metals that enables that particular application? That's the question. Just discuss with one another. You take any example, don't be shy. So you can think about another application. Yes?
Like, I'm thinking there's the car body, the metal.
Yeah, bodies of cars. So what about bodies of cars? Should they be impact resistant? Absolutely. And you wouldn't have that particular kind of structure unless and until metals were malleable. So they are malleable, they are impact resistant, correct? They don't deform that easily, so they have a high Young's modulus, correct?
Corrosion resistance?
It depends. So the alloy that you choose should be corrosion resistant, absolutely. Very good. All those are very good answers. Yes. Any answer? Just don't be shy. Yeah.
To prevent lightning, we used to put art thing for metals.
Very good. So that's also related to electrical wires. So what he's saying is that for earthing, see, you might actually have in any given socket an earthing connect as well, right? So for that earthing connect, Ultimately, there should be a wire that carries it to the earth. Otherwise, you do not have a real ground. All potentials are with respect to some ground. All potential differences means that there should be some reference point, right? So you need a ground. So absolutely. So in order to define the ground in the context of your electrical sockets in your home, you can have the grounding point and you can basically connect it to the ground, and that is an electrical wire, no question about it. And there you are using the conductivity, okay, of electrical wires. Very good. Now let us go to the next category of materials, ceramics and glasses. They have high Y. What is Y? By now you should know what Y is. Y is Young's modulus. Very good. Y is stress by strain. In the case of metals, what were the values? 4 to 400 GPa. What is the value when it comes to ceramics? I have written the value there. 150 to 450 in what units? But is it under tension or compression? So it has low tensile strength. It has high Y, 150 to 450, but it has low tensile strength. That is funny, isn't it? So how can you say that something has high Y, high Young's modulus, but you say that it has low tensile strength? What strength are they talking about? How can you actually reconcile between these two? So what is the unit of that tensile strength? Again, stress, correct? So what we are saying is this ratio can be high, but the absolute value that you apply before you see failure, do you need to go till this value? See, this ratio is 150 to 450, but the stress that you apply before you actually see the material rupturing, coming apart or failing in some form, does it have to reach this value? Does it have to reach this value? Certainly not, not required. Not required. And you see, it fails much more easily than metals. Much more easily than metals. That is because cracks can develop. These are brittle materials. So you take a chalk, you take a piece of chalk, you open it up, it actually comes into two halves. That doesn't happen if you take a wire and pull it. It doesn't come apart into two halves, right? So you will notice that the Young's modulus is fairly high, but the tensile strength, the limit, is fairly low. It's only 400 megapascal. So it is basically 1 by 1000th this. So the ratio is very high, yes, but the absolute limit of this is not very high. There's a difference. Do you understand this difference? Do you understand this difference? The limit of the numerator is quite low, but the ratio is fairly high. Is that allowed? Is that allowed? Correct? That's totally allowed, right? But look at the next thing. Its compressive strength, on the other hand, is fairly high. It is about 10 times higher. So in tension, ceramics don't behave very well. You take a chalk, you press it against itself. It doesn't come apart. You pull it, it comes apart. So its strength in tension and its strength in compression can be very different. And its strength in compression is 10 times higher than the strength in tension. In tension, it barely survives 400 MPa max. Okay, in compression, it goes up by 10 times, 4000 MPa. You understand? Now, would you say that this chalk is either ductile or malleable? This chalk that I am talking about, brick, okay, clays, are they either malleable or ductile? Certainly not. They are not malleable, nor are they ductile, right? Very good. And high melting points. Does that make sense? Ceramics, they have high melting point. Does it make sense? Can you give me one example wherein ceramics are used for a high temperature application? Can you discuss with one another? And I'll give you a hint.
That fuse for fuse.
Huh?
That for fuse you are using the ceramics.
Exactly. So the metal, of course, fuses. The ceramic doesn't. Can you give another example?
We are using in oven you are using ceramic fuse.
Absolutely, yes. For cooking, you use ceramic pots and porcelains and so on. Nothing happens. So ceramics tend to have very high melting point. They remain solid for a very high temperature. Very good. Next, what are the melting points? 2000 to 4000 degrees Celsius, very high temperatures, all right. So ceramic linings usually survive for very high temperatures. Okay, not just ceramics, even materials like graphite, for example, can survive very high temperatures. Molybdenum and tungsten survive very, very high temperatures also. They are metals. Usually they have low creep resistance, but molybdenum, tungsten, etc., they are generally better in their creep resistance, their melting point, and so on. That is why they are used for high temperature applications. But most of the,
All carbide also.
most carbides, very good. So many of these carbides, graphite, okay, molybdenum disulfide, many of these ceramics have high melting point. They can be deployed for high temperature applications. They are thermally resistant, okay. So, and there are a few exceptions even from the world of metals, as I told you, tungsten, molybdenum, and so on, which also survive fairly high temperatures, all right. And then there are some nickel based alloys that are creep resistant at very high temperatures. Most metals have poor creep resistance, but some nickel based alloys have fairly good creep resistance, all right. So there are always exceptions to these classifications, all right. So these should be seen as relatively soft classifications as a consequence. Poor machinability. What does poor machinability mean?
If you want to machine into some certain
Shape, yes. So in fact that is the reason why you know, there is an entire art called sculpture, right. So you have stones. Stones are usually made up of silicaceous compounds. They are ceramics. They have very poor machinability. That is why it takes sometimes months to carve a sculpture. It takes months. So it's poor, an example of poor machinability. All right, it's not easy to machine ceramics. Next is good temperature and oxidation resistance. Can you give me one example wherein its temperature and oxidation resistance is used? Give one example of a ceramic, okay, the application of which is enabled by its oxidation resistance. Yeah, why don't you discuss with one another? Why don't you just discuss with one another? Just discuss with one another. I'll come to each one of you. Do you understand the question? Just one application of ceramics. You can also mention the name of the ceramic if you know, or you can say I know that ceramics are used in XYZ application, and that is because it has oxidation resistance. Okay, do you understand the question? So the Swayam viewers might note that one of the nice ways to actually engage with the students is by asking them questions and going around and giving them hints so that they can solve problems by themselves, get a better understanding and handle of what you are talking to them about, and so on. So I highly encourage student-led discussions, guided discussions, and using guided discussions as an opportunity to engage with students. This also allows you to actually spend time with students who might be falling off cracks. Okay, so do you have an application in mind?
Like quartz glass.
Quartz glass, very good. What is the application?
We can use it at high temperature also.
Yes.
It can avoid for oxidation.
Yes, so you can actually use it as a beaker or whatever in your chemistry lab, and the reason is because it survives high temperature, right? And is it a fairly good thermal conductor or a poor thermal conductor? So why don't you, because I gave you a homework question and you mentioned, so look at the thermal conductivities of metals, write it down, and write down the thermal conductivities of some common ceramics. In your case, you actually mentioned quartz. Similarly, you can say borosilicate glasses. Whatever, you just write down some examples so that in the next class we can discuss that. Okay. All right, so I will take 2 more minutes to now go through this. All right, so oxidation resistance, this is your homework. You will think about an application and we'll start off from there, and some numbers that you will actually probably get from your searches. Not only that, it should be very obvious to all of you, ceramics are very hard. That means they resist deformation, right? They have high specific heat capacities and densities comparable to metals. So they are fairly dense. Bricks are dense, isn't it? Bricks are heavy, they are dense. Usually crystalline. And this is an important thing. not all ceramics are crystalline. Glasses, for example, are non-crystalline. There is no real atomic ordering except some short range order in the case of glasses. Bonding type tends to be mixed. Even carbides, the one that you mentioned, can have a mixture of ionic as well as covalent bonding. Covalent bonding tends to be highly directional. Ionic and metallic bonding is not very directional. What these bonding types mean, we will see in the next, shortly, maybe in a few classes from now. And then some of them are very good candidates for superconductors and a wide range of applications including energy storage, okay, sensors and actuator materials that are demonstrating ferroelectricity, piezoelectricity and so on. So these are some specialized effects. I don't expect this to be known to students at the first year level, but by and large it's important for you to know that these effects are actually relevant for making sensors and actuators. But however, they do have poor shock resistance. They actually come apart. If there is an impact of a car, the window shatters, and that is actually evidence of the fact that they have poor shock and impact resistance, and they can have wide range of band gaps. Some of them in fact surprisingly are conducting. Okay, some nitrides, for example, are known to be conducting. Certain sulfides are conducting, but many oxides are non-conducting. Alright, so now we come to the last part of the class. So can we just spend 2 minutes discussing and then helping me come up with a summary, okay, of what we have discussed so far. Alright, yeah, I'll write down that here. So you can go through the handouts and underline things that you think is important to summarize. Alright, and you can help me make a summary for today's class. So why don't you discuss with one another also, because from each table I want just one person to respond. So this is nice, you are telling him to write down what you think is an important point for summarizing. You can discuss with him. So you can write down and you can tell me. Yeah. So can I have some summary statements? Yes. Can I start with that table?
We started with what is the classification.
Yes.
Then how it is relevant.
So what are some of the classifications you learned? Metals.
We have given example of periodic table.
Yeah.
Various.
So very good. So I am ahead of you here. I went out of step. So we learned what classification is and definition and uses, right? All right. Very good.
And we have learned some of the attributes of metals and ceramics.
Very good.
And we have discussed the relevant applications
Yeah.
based on the properties of these metals and ceramics.
Wonderful. So we connected the application to the property, right? So we tried to look at properties that enabled some specific applications. Very good. So that is what we looked at. And from an andragogy pedagogy standpoint, what we discussed today was the following. So let me pull this out. We started today's class by again observing this ambience and asking a few questions that are important for teachers who would like to live an introspective life and conduct introspective lessons. For example, how would we change our own classroom setting? Do we give time to students to reflect, to learn, to absorb the lessons that we teach them? And how do we think about large classroom management? That's going to be a dangling question for a long time. But nonetheless, it is, I think, important for teachers to think about this. Over and above that, I also told about the importance of this active cooperative learning and how this can be an enabler for the teacher to actively engage with the students as well. And in particular, intervene in a manner so that students who might be falling off cracks can actually be supported so that they can come back and be on the same page as the rest of the class. So that's all there is for this session. So thank you very much. We'll return shortly. Thank you.